Okay, class, today we are going to introduce the concept of random processes. Let's start with a quick reminder from our discussion on random vectors. For an arbitrary index set t and a real valued function x, which is an element of r to the t, meaning x is a collection of real numbers indexed by t, the projection operator p sub t, mapping from r to the t to r, simply extracts the component corresponding to the index t. So pi sub t of x equals x sub t. Now for the definition of a random process, let omega script f p be a probability space. For an arbitrary index set t, which often represents time or space, and a state space script x, which is a subset of r, a map x from omega to script x raised to the t is called a random process if the projections xt from omega to script x defined by omega maps to xt of omega, which is p sub t composed with x evaluated at omega, are random variables on the given probability space for every t in t. This leads to the definition of a sample path. For each specific outcome, omega in our sample space, omega, the function x of omega, which maps from the index set t to the state space script x, is called the sample path or the sample function of the process x. So for a fixed omega, x omega is a deterministic function over t. As a reminder, a random process x defined on a probability space omega script f p with an index set t and a state space script x, a subset of r, can be viewed in a few different ways. A, as a map x from the Cartesian product omega cross t to script x. So x of omega, t is a value in script x. B, as a map x from t to script x raised to omega. This means it's a collection of random variables xt, each mapping omega to script x indexed by t in t. This is often the most common way to think about it. C, as a map x from omega to script x raised to t. This means it's a collection of sample functions x of omega, each mapping t to script x indexed by the random outcome omega in omega. We can classify random processes based on their state space and index set. The state space script x can be countable, corresponding to a discrete valued process, or uncountable, corresponding to a continuous valued process. If the index set t, which is a subset of r, is countable like the natural numbers or integers, the stochastic process is called a discrete time stochastic process or a random sequence. When the index set t is uncountable like an interval of real numbers, it is called a continuous time stochastic process. It's important to note that the index set t doesn't always have to represent time. If the index set is a spatial domain, then the stochastic process is referred to as a spatial process or a random field. And if t is something like r to the n cross half open set 0, infinity space and time, then the stochastic process x is a spatiotemporal process. Let's consider some examples to make this clearer. For discrete random sequences, discrete time, discrete or continuous state space, think of brand switching behavior over weeks, discrete time queuing systems, or the number of people visiting a bank each day. For continuous random sequences, this seems to mean discrete time but continuous state. Examples include daily stock prices, currency exchange rates, the waiting time in a queue for the nth arrival, or the workload at arrival instances in time-sharing computer systems. For discrete random processes, continuous time, discrete state space, counting processes like the Poisson process we'll see later, a population sampled at specific birth or death instance, or the number of people in a queue observed over continuous time. For continuous random processes, continuous time, continuous state space, the water level in a dam over time, the waiting time until service for a customer arriving at any point in time in a queue, or the location of a mobile node in a network as it moves continuously. Now let's discuss measurability for random processes. A quick note: for a random process, x mapping from omega to script x raised to t defined on omega script f, p we know by definition that the projections xt, which is pi sub t, composed with x are script f measurable random variables for each t. Therefore, the set A xt of x defined as xt inverse of half open set minus infinity x must be an event in script f for all t in t and all real x. This leads to the definition of measurability of a random process itself. A random map x from omega to script x raised to t is called script f measurable if axt of x, which is xt inverse of half open set minus infinity, x is in script f for all t in t and all x in R. This is essentially what the definition of a random process already states. Now let's define the event space generated by a random process. The event space generated by a random process x from omega to script x to the t defined on a probability space omega script f p is given by sigma of x, which is the smallest sigma algebra generated by all sets of the form A xt of x for all t in t and x in R. We can also define the projection of the random process x onto a subset of its components. If S is a subset of the index set T, then XS is a random vector mapping from omega to script x raised to S, where XS is simply the collection XS for S in S. Some reminders on measurability: recall that pi sub t inverse of half open set minus infinity x, where pi projects onto the tth coordinate of a function in script x to the t, is the set of all functions in script x to the t whose tth component is less than or equal to x. This can be thought of as a cylinder set, the product over S in T of half open set minus infinity xs, where xs equals x for s equals t and xs equals infinity for all s not equal to t. The script f measurability of the process x implies that for any countable subset s of t, the joint event axs of xs defined as the intersection over s in s of axs of xs in script f for any xs in script x raised to s. This is because script f is closed under countable intersections. We can try to define ax of x as the intersection over all t in t of axt of xt for any function x in R to the t. However, this ax of x is only guaranteed to be an event, i.e. in script f, if the set S defined as t in t such that the tth component of x, t of x, is less than infinity, is a countable set. This is because sigma algebras are only guaranteed to be closed under countable intersections, not uncountable ones. In the case where S is countable, then ax of x, which is the intersection over t in t of axt of xt, simplifies to the intersection over S in S of axs of xs. This is axs of xs, which we know is in script f. Let's illustrate with an example, a Bernoulli sequence. Consider the sample space omega equals ht raised to n infinite coin tosses. We define a mapping x from omega to 0.1 raised to n such that xn of omega is the indicator of h for omega ni1 if the nth toss is h0 if t. This map x is a script f measurable random sequence if each component xn from omega to the set containing 0.1 is a bivariate script f measurable random variable on the probability space omega script f p. Therefore, the event space script f must contain the event space generated by the sequence of events E, where En is defined as the set of omegas in omega such that xn of omega equals 1. This is the same as the set of omegas where the nth toss omega n is h. Each En must be in script f for all n in n. That is, the sigma algebra generated by the random process x sigma of x is equal to the sigma algebra generated by the sequence of events E sigma of E, which is sigma of the set of all En for n in n. Now let's talk about the distribution of a random process. For a random process x from omega to script x to the t defined on omega script f p, we define a finite dimensional distribution FDD fxs mapping from R to the S to closed interval 0.1 for any finite subset S of t. This is given by fxs of xs equals the probability of axs of xsp of axsxs for any xs in R to the S. AXSXS is the event XS lesser than or equal to XS for all S in S. Consider an example, a probability space omega script FP defined by the sample space omega equals the set containing HT to the N, the event space script F equals sigma of E, where En is head on nth toss, and a probability measure P from script F to closed interval Z0.1 defined by P of intersection for I in F of E, I equals P raised to the cardinality of F for all finite subsets F of N. This describes a sequence of independent Bernoulli trials. Continuing this example, let X be a random sequence from omega to set 0.1 to the n, defined as xn of omega equals the indicator of En for all outcomes omega and all n in n. For this random sequence, we can obtain its finite dimensional distribution fxs from R to the S to ZF1 for any finite S subset of T, here T equals N, and any X in R to the S. Let I naught of X be the set of indices I in S such that Xi lesser than 0 and I1 of X be the set of indices I in S such that Xi is in interval 0, 1 inclusive of 0 and exclusive of 1. Then fx s of x is 1 if both I naught of x and I 1 of x are empty, i.e. all xi greater than or equal to 1 for I in S. It is 1 minus p raised to the cardinality of I1 of x. If I naught of x is empty, but I1 of x is not empty, all xi greater than or equal to 0. And for those in half open set 0.1, we need xi equals 0, which has probability 1 minus p. And it's 0 if I naught of x is not empty, i.e. at least one xi lesser than 0. This is equation 1. Now let's consider the joint distribution over the entire index set T. We are interested in identifying a joint distribution f from R to the T to closed interval 0, and 1. To do this, for any function x in R to the T, an assignment of a real number to every index in T, we would need to know fx of x defined as p of the intersection over t in T of omega in omega such that xt of omega lesser than or equal to xt. This is p of the intersection over t in T of xt, inverse of half open set minus infinity xt, or p of a x of x. As we discussed, ax of x is guaranteed to be an event in script f only when the set of t in T for which xt is less than infinity is countable. For a simple independent process with a countably infinite T, any function of the above form, the joint CDF would typically be 0 if xt is finite for all t in T, unless p of xt lesser than or equal to xt is 1 for all but finitely many t, which is rare. Therefore, in practice, we usually only look at the values of fx of x for x in R to the T, where the set t in T such that xt lesser than infinity is finite. This essentially means we are always working with finite dimensional projections. The set of all finite dimensional distributions, FDDs, of a stochastic process x from omega to script x to the T characterizes its overall distribution completely. This is a fundamental result by Kolmogorov.
Let's revisit our example to illustrate this. Consider the probability space omega script f p with omega equals ht to the n, script f equals sigma of e n is head on nth toss. Let x be the random sequence from omega to set 0.1 to the n, where xn of omega is the indicator of en.
For this random sequence, if we are given its finite dimensional distributions fxs from R to S to closed interval 0.1 for any finite S subset of T equals n, as defined in equation 1 in terms of I naught x and I1 x. Then from these FDDs, we can recover the underlying probability measure P on script f. For example, we can find P of intersection for I in f of E, I equals P to the power of cardinality of f for all finite f subset of n. Now let's define independence for random processes. A random process is said to be independent if the collection of event spaces sigma of xt for t in T is independent. This means that for any finite subset S of T and any choice of levels xs in R to the S, the joint CDF f xs of xs, which is P of the intersection for S in S of xs lesser than or equal to xs, factors into the product of the marginal CDFs. The product over S in S of P of xs lesser than or equal to xs, which is the product over S in S of fxs of xs. A remark here, the independence of a random process is equivalent to the factorization of any of its finite dimensional distribution functions into the product of the corresponding individual marginal distribution functions. Let's see an example of an independent random process. Consider the probability space omega script f P with omega equals set h t to the n script f equals sigma of e n is head on nth toss and p defined by p of intersection for I in f of e I equals p to the cardinality of f for finite f. Then the random sequence x from omega to set 0.1 to the n defined by xn of omega equals indicator of en is an independent random process, a sequence of IID Bernoulli P random variables.
Finally, we can define independence of two stochastic processes. Two stochastic processes x from omega to script x to the t1 and y from omega to script y to the t2 are said to be independent if their corresponding event spaces sigma of x and sigma of y are independent.
As a remark, this implies that for any finite subsets S1 of T1 and S2 of T2 and any x in R to the S1 and y in R to the S2, the events AS1 of x defined as the intersection over S in S1 of x, S inverse of half open set minus infinity, x, S and B, S2 of y defined as the intersection over S in S2 of ys, inverse of half open set minus infinity, ys are independent. Consequently, the joint finite dimensional distribution of x and y factorizes P of AS1 of x intersected with B S2 of y equals P of AS1 x times P of B S2 of y. This is Fx S1 of x times Fy S2 of y. This concludes our introduction to random processes, their classification, measurability, and the crucial concepts of their distribution and independence.